In this video tutorial, we're going to go over the fundamentals of shading and an introduction to using Substrate in Unreal Engine 5.7. Substrate is a next-generation shading system and workflow in Unreal Engine that will replace the current PBR workflow. As of Unreal Engine 5.7, Substrate is now considered production ready. This video is going to be great for anyone new to shading or new to Substrate, because if you're used to using that metallic and that whole PBR workflow, when you create a substrate slab or a substrate material, you have quite a few different parameters, which might be a bit confusing. So this video is going to cover three crucial things to understand. First, we'll go over and make sure we all understand the PBR workflow and its methodology. Second, we will then go over the benefits that Substrate offers over PBR and why it is replacing the old shading workflow. And finally, we're going to go over how to create a few different materials utilizing Substrate, making sure we understand its workflow. Now, what I need you to do before we jump into this is to hit that like and subscribe button and let me know down below in the comments if you want to see more videos about Substrate and advanced material creation. So let's first start with PBR. Physically based rendering, or the PBR workflow, is the most well-known and familiar term that almost everybody in computer graphics is familiar with. PBR replicates how real-world materials would interact with light. This starts with its core principle, which is energy conservation, which is the idea that a surface cannot reflect more light than it receives. Depending on the surface, light is either reflected or absorbed. For example, in this case on the left here, we have a mirror or a chrome ball that reflects almost all the light it receives. Whereas on the right side of the screen here, we have a dark asphalt, which absorbs most of the light it receives, only reflecting a very small amount of that light. So if you think about a PBR workflow and what parameters you set to define your material, one of the key parameters is your color map or albedo map. And what does this truly control? The color map represents the intrinsic color of a surface. What you would see if that surface had completely even lit lighting that's perfectly diffuse and you have no reflections. So pretty much it's underlying surface color. Now, one thing to keep in mind with the PBR workflow is we also have controls like metalness or metallic. So in Unreal, we have a metalness control to determine whether a surface is a metal or a non-metal. And this changes the way your diffuse color, base color gets used as well. When a surface is a metal in the PBR workflow, generally the base color becomes your reflection tint. So if you're making gold or something, you would change your base color to be slightly tinted more yellowy, orangey, to tint the reflection of that surface. And that's a big difference. When we look at metals and non-metals, like this chrome ball here, which would be a metal, or this asphalt or concrete ball, which would be a non-metal, they reflect light very differently. So if the surface is a dielectric or a non-metal, a non-conductive material, like this asphalt or concrete, it only reflects a very small fraction of light directly as specular reflection at the facing angle. And in most cases, it's somewhere between 4 to 7% or so. Whereas with metals, it reflects a much greater amount of light as specular reflection at the facing angle. Now with the concrete or the asphalt here, the rest of that light that doesn't get reflected scatters into the material, resulting in diffuse reflection. So to summarize, like in the PBR workflow, if a surface is a conductor or a metal, it reflects most incoming light as specular, and the reflection is tinted with the albedo or base color. And to determine whether a surface is a metal or non-metal, we have that metallic or metalness control. Now, if we have surfaces that have a mix of those two different things, this is generally why we also have a range of metalness to use. In real life, everything's either metallic or it's not. Like it's either a conductive surface or it's a non-conductive surface. But sometimes when doing that in VFX or in your surfaces that you're painting, you might get some weird edges. So sometimes they'll use values in between 0 and 1 for metalness, which isn't technically correct, but it can help blending two different materials together. Like if you had rust on top of metal, or if you had something that's a non-metal on top of metal, just to avoid like weird edges and stuff. So sometimes you have to cheat to get surfaces to look the way you want. Now that we understand how different materials reflect and absorb light, what about the distribution of reflection? Generally, all surfaces in the real world have some amount of reflection falloff, or Fresnel. Now, Fresnel describes the amount of light that's reflected based on the viewing angle. So generally, the facing angle reflects less direct or specular light than the grazing or side angle. In this case that we're looking at right here, metal surfaces, like when the surface is a metal in the PBR workflow, it reflects a lot more specular reflection at the facing angle, generally about 60 to 100%. But most metals are probably in like the 90% range. And non-metals generally reflect about 4 to 7% as specular reflection at the facing angle. And pretty much almost all materials reflect 100% or close to it at the grazing angle, at the completely side-facing angle. So just to make this clear, this would be the facing angle, the angle that we're looking at. And the grazing angle would be the edge, or the angle that's facing away from us. So a way you could think about this in real life and kind of make sure that you kind of understand this is think of a rain puddle. If you look at a rain puddle forward facing, directly down looking at it, you kind of see kind of through it, or you don't see it as like mirror-like. It's not reflecting that much light. But if you tilt your head to the ground and you look at a puddle from a very side angle, then it tends to reflect a lot more light. What about roughness in the PBR workflow? If I have this chrome material here in the PBR workflow, base color is white, it's defined as a metal, like its metallic value is set to 1, and its roughness is 0, it's a very smooth surface. The reflections are very sharp, and this is a very important thing to understand, is our roughness is how rough a surface is, or how smooth it is at a very fine level. If we want to add roughness, we could add a normal map to break up the surface. We could add a bump map. We could add displacement, or even model the surface to have more breaks and dips in it. But the roughness control allows us to define how smooth or rough the surface is at a very, very fine level, kind of down to like the micro facets of that surface. So if you have no roughness, the surface is very smooth. It's less chaotic. Whereas if we have more roughness, maybe like 0.3 here, the reflections become very, very blurry. And that's because the surface now is more chaotic from a very fine level. It's more rough and it's breaking up those light reflections. Now, one thing we should understand is PBR does a lot of things right. It gives us a fast, efficient, and physically grounded foundation for some realistic shading. But it's built on a very fixed and simplified set of models that make it efficient but limited when needing to do more complex materials, or specifically layered surfaces. So PBR does not simulate optical interference. It doesn't really support mixed materials properly. You can have materials mixed in the PBR workflow using masks, wetness on top of something, or oil on top of something, or having a clear coat on top of something, but these things are generally approximated in a PBR workflow. And this is where Substrate excels. Substrate is a shading framework or workflow that kind of allows for more of a modular system where you can stack and blend multiple materials where each layer behaves more physically correct. It's not perfect either, but it's a step in a direction that brings you closer to a more accurate result. So let's go over creating a few different materials with Substrate. The first thing we'll have to do is enable Substrate. So in the latest version of Unreal, which is currently 5.7, you can go to Edit, Project Settings, and you can search for Substrate. And when you search for Substrate, the very first checkbox that you'll need to turn on here is the one that says Substrate Materials. There are a few other options that are experimental and a little bit more advanced. If you want to enable certain features, you don't have to turn these on, but if you want to have some of these features enabled, you can. There is one setting here for Substrate Advanced Visualization Shaders. That's more for debugging shaders that you can turn on, and that currently only works with DirectX 12. So we can enable Substrate materials, and then we'll have to restart Unreal for the changes to take effect. But once you have that done, you should be able to then go to your content browser, create a material as you normally would create one. And if I just call this m_substrate and I open it up, we have our normal material preview window. Nothing looks really different. The only thing that you should notice is there's a front material here, and you'll be able to create substrate nodes. So if you search substrate, you'll find all these additional nodes. And a substrate slab is kind of the most basic substrate node for creating a simple material. So we can then connect that output to our front material, and all these other parameters go away, and this becomes our substrate material now. And you'll notice the substrate slab has a lot of additional parameters, and I'm not going to go over those right now, but if you are part of the Patreon, you'll get access to a PDF that goes over a little bit of a description of what each one of those slots or parameters does. But we'll go into that eventually. The main thing I want to go over right now is about the F0 and F90 that we have here. The F0 parameter and F90. You'll notice that we no longer have metallic or metalness. Instead, we have this F0 and F90. And the F0 is a specular reflection at the facing angle. F90 is a specular reflection at the grazing angle. And if we hover over F0, you'll see that it says the default values are plastic, or 0.04. That's kind of what we just talked about, where non-metals have roughly a specular reflection at the facing angle that's roughly about 4 to 7%. So this defaults to 4%. And then the grazing angle, the 90-degree angle, the angle facing away from us, you can see here defaults to 1 or 100%. And that's kind of the default for it. Now, if you did want to use the metalness workflow, if you did have a metallic or metalness map and you want to plug that into Substrate, there are nodes for that. So there is, if you search metal, you'll find Substrate Metalness, and that will allow you to take your metallic map, your base color, and then output these into diffuse, albedo, and the facing angle. Now you can see the grazing angle stays untouched because that's pretty much always 100%. So if we were to use this now and try to create some gold material, it's very similar to the PBR approach. We can just create a constant, set that to 1. So we could say this is a metallic material. The base color becomes the color we want to tint our metal with. So for gold, gold reflects more kind of yellowy tones. So maybe something like that. And then our roughness, gold's not super smooth, has some scratches. It's a soft metal, so maybe we can make that a little bit more blurry. And we kind of have the start to our gold material. And you could change that color. If you wanted steel, steel tends to lean a little bit more of a light blue tint, maybe not that much. So you could do something like that for steel, and you get more technical with these values. It all comes down to, in real life, what wavelengths does that material absorb and what wavelengths does it reflect. So gold generally reflects more red and absorbs more blue wavelengths, and that's what gives it the tint. Now, we could also do this without the metalness, or without the substrate metalness. The other way we could do it would be kind of the way you could do it in film. You could make the reflection for the facing angle be very bright, and also be tinted. And then you'd set the diffuse to be pretty much black. And you'd have your roughness, maybe a little bit more blurry, but there we go. Same kind of thing. is doing pretty much the same thing, but just not using the metallic workflow. So same material, two different ways to approach it. It doesn't really matter which one you use. At the end of the day, it's doing the same thing technically. So if you have metallic map, you could use that node. If you don't, you could also just do it the way that I just showed. Now, one last thing I want to talk about before we move forward and create some other materials. This F90, determining the reflection at the grazing angle, which is mostly almost always 100%, is kind of not as accurate as determining it at a different angle. There's a possibility they might move to F82 instead of F90. Instead, you define the reflection at the 82-degree angle facing away from you, not at the full grazing 90-degree angle. And why would we want to do that? If you look at what Adobe is doing, they use F82 for their specular edge color. So I just brought this up to kind of show that. So Adobe uses their specular edge color as the 82-degree angle tint. And why would they do that instead of a 90-degree angle? It's mainly because the 90-degree angle is always like 100% reflective, most of the time. So any color that the underlying surface has, or any tint that might be caused by a specific type of metal, won't be as properly described at a 90-degree angle. Because at that point, it's almost completely 100%. It's most likely leaning towards like white and not tinted. So by defining it at the 82-degree angle, it contains a little bit more subtleties that the underlying material has. So you get a better and more accurate representation of overall what that material is doing on its reflection fall off. So something that Unreal might eventually move towards. But just wanted to bring that up so everyone's kind of aware of what F90 means and why Adobe is using the F82 tint color for their specular edge color. Now, one last thing to jump back to, even if you're using the PBR workflow. So I'm just going to go back and delete the substrate slab for a second. So in the PBR workflow, you have the specular parameter. Leaving that at 0.5 kind of does the same thing. It makes the reflection at the facing angle for non-metals roughly about 4%. If I were to push that up, it increases that. So it gives us more specular reflection at the facing angle and less diffuse. So that's kind of like a little bit of a nudge to kind of offset that. You won't notice it here with such a simple material. It's not that shiny, but that works as just kind of like a strength control for your specular reflection to make it a little bit brighter, a little bit darker for non-metals. You'll notice the substrate slab says BSDF down here. So this will kind of tell us what our material essentially is. If we have material that we need to make as translucent or subsurface scattering, we're going to see different little tags pop up down here. So this is something that's very useful to look at. And on our substrate slab, we have these subsurface type options. By default, it's set to diffusion, which says diffusion-based subsurface scattering. But if you were to make something like glass, you'd have to change this to a simple volume. So you can see if I hover over a simple volume, it says approximation of optically thin slab, e.g. glass. So where light is visible through the material. So let's try that as our next exercise. Let's make a glass material with substrate and talk about what we need to do for that. So the very first thing we have to do is we have to go to our main material node here that we plug our slab into. We have to change this from blend mode. Now, generally without substrate, if you're shading a PBR in Unreal, you're probably used to changing this blend mode to translucent if you want to do something like glass. With substrate enabled, you will not have translucent. You will have translucent gray transmittance and colored transmittance and translucent colored transmittance. You're going to have a couple different things here. So if you want to do something like tinted glass, you probably want to do translucent colored transmittance. If you're just doing non-colored glass, then you can do translucent gray transmittance. So maybe we'll do that for now. And the next thing we're going to do is go to our slab and set it to be simple volume. And that's kind of how we can start setting up our glass. Now this doesn't look like glass just yet because there's a few more parameters we'll have to change. So one of the other things we're going to adjust is, we'll notice here it says refraction disabled. We need refraction on our glass material for it to distort the background behind it correctly. If you look through glass or you look through water, the background becomes distorted. And this is because those surfaces slow down or speed up the light as it passes through, causing distortion, causing that effect that we see. And this is defined with index of refraction for our material here. And right now this refraction is disabled. So we're going to go on here, we're going to search for refraction, we're going to set the refraction method to index of refraction, which is technically the most accurate, but it's not going to be perfect at real-time speeds. It's not going to work exactly as it should in lit mode. In Path Tracer, it'll work a little bit better, but it'll give us generally a correct result. Now, there are other ways you could cheat it here using pixel normal offset or 2D offset, but for now, we'll just use index of refraction. And the index of refraction for something like glass is probably about 1.4, and that varies dependent on the glass, but generally water is 1.3 repeating, and something like glass is probably 1.4 to 1.5. So we'll start off with that. So what this SSS MFP is going to do is it's pretty much the average distance light travels inside a material before being scattered or absorbed. So you can think about it almost as kind of the perceived thickness of a material. It'll affect how much light is absorbed and scattered within the material. And this value, most of these scales and things here are defined in centimeters. So it is based on real world scale. And the way that we're going to use this is by creating a node that's going to help us more easily set our transmittance for this material. So I'll create my transmittance to mean free path node, connect the MFP to the SSS MFP, and next we have to set the transmittance color. You can see already it's kind of looking see-through, but we need to set our transmittance color. And since I'm not doing tinted glass, I'm just going to do something like 0.98. It's like 98% on red, green, and blue, or X, Y, and Z, whatever you want to call it, but we know it's a color, so red, green, and blue. And that still doesn't really look like glass. A few other things we have to do. So one of those other things we have to do is to get proper shading on here, we need to change the way it's being shaded. So on our M substrate node here, currently for translucency, it's using the lighting mode of volumetric non-directional. And that's not going to give us good looking glass. It's not going to give us specular reflection on glass. If we want really good looking glass or water, we should probably use surface forward shading. And that's going to be more demanding, if not the most demanding here, but it will give us the best result. Like if I go to that, hey, this looks like pretty good glass, but by going to subsurface forward shading, I get even better reflection highlights. I get like the actual speck ping or highlight that we can see here, whereas surface translucency volume, we don't get that. So I'll go with surface forward shading for a lighting mode. It is the most demanding. It's not what you need in all cases, but I'm trying to show, the best looking glass we can get here with Substrate. Now let's check out our IOR. We set that to 1.4. Let's put this glass over the background and see what it does. And you can see it's distorting that background there. And if it were to change this IOR, it will change the distortion. Higher values, like 2, going to magnify it more, give it more distortion. Lower values are kind of accurate to like 1. Anything below 1 kind of breaks it. 1 is essentially air. Air doesn't really distort or speed up or slow down the light rays that go through it. So if you set this to 1, you pretty much get like no distortion. Now for glass, 1.4 is okay, maybe 1.45. That kind of feels a bit more like what we'd expect from glass. Now if I save this and put it on some more complex surface instead of this ball here, we can see how it looks, and this looks a little bit wonky. Like, we see the weird sphere inside of it kind of refract and reflect here, and it doesn't feel like the glass is doing something right. So this is a little bit of a problem that we're going to run into. And this is because refraction in real time is not going to be accurately calculated. It's relying more on screen space information and not properly ray traced. So on surfaces that are simple, it might work, but something more complex like this, it's not really going to work. So I'm going to show you a workaround, how to get this material to look more realistic on something like this, on a more complex shape. But first, let's maybe compare it against a more physically accurate result. So I want to switch to path tracing, but you're going to notice one thing. If I go to path tracing mode, hey, this no longer looks like glass. And that's because we need to set a very important parameter for this to work in path tracing. So the reason why it looks like this is because we haven't set our MFP scale. So it's assuming that this material is 0, which essentially means infinitely thick. And it's going to make it look like a solid surface instead of a glass. So to fix this, we need to go set our MFP scale. So we'll go in here and set our thickness. Now our thickness is specified in centimeters. So maybe for this glass, I'm going to set it to 2 centimeter thickness. And once I've done that, I'll then connect my thickness to the SSS MFP scale, and I'll save our material. And now if we go back and we go and look at our path tracing mode, that starts to feel more correct. That looks like glass, or what I'd expect this glass shape to look like. And you could see the ball inside is kind of a little bit distorted by the glass. The glass is distorting, the background. But when we go to lit mode, that doesn't really look like the same refraction. So our refraction with path tracing is going to be more accurate. With the lit mode, it's going to be cheated based on screen space things and not properly ray traced. So how can we compensate for that? There's a little bit of a trick or a cheat that we can do. What we're going to do is we're going to open up our material. We're going to go to the refraction IOR. And what we're going to do instead is cheat a little bit. We're going to create a lerp, which is like a blend between one value and another based on a mask. And the mask, we're going to use a Fresnel node, which gives us a nice fall off from the edges to the facing angle. And maybe I'll customize and just set this to something that I think will work good for this. But what we're going to do is blend between different IOR values to cheat it to look a little bit more physically correct, since we can't really get proper good refraction in real time without doing something a bit more advanced, without having to, do something that does a lot more intensive ray tracing. So what we're going to do is just use this Fresnel node as the alpha of a lerp between A and B. The A value is going to be 1. The B value is going to be 1.45, our glass value. And this is just going to give us that distortion around the edges. So maybe on a ball it looks a little bit weird, but on our kind of more complex shape, this starts to look a little bit more correct. Even though it's totally not, it feels better than what it was before with just having that IOR value. So this is something you can do to cheat it. You can blend between a different IOR from the facing angle to grazing angle to still get a bit of distortion in your glass, but not have it kind of totally break when you have something inside it like this. And now if I go to path tracing, the IOR looks all messed up because it's still using those values. So if you have a scene where you have to switch from lit to path trace and kind of have to have it work in both, usually you commit that your scene is going to be all path traced and a short film or something, or it's going to be real-time rendered and fully interactive. But if you have a case where you have to support lit and path traced, what you can do is use the path tracing quality switch, and then you can define what happens when you're real-time or normal and what happens when you're path traced. And then what you can do is have it go down those different paths based on what you're doing for rendering. So doing that, you can then get the best of both worlds. Now, thickness is very important. If we want to make a more smoky kind of glass, we could up this thickness. We can make it a thicker surface and have it look more like it has kind of darker detailing where areas become thicker. We can also change the color here. Right now it's at 0.98, but if I do something like 0.9 instead, whoops, 0.9, 0.9, 0.9, and we save that, it's going to make it look more like a darker glass. So if I go here, I don't notice much, but if I go to path tracing, it looks more like a smokier kind of gray kind of glass. So that color is going to change also how our glass looks. If I go in here and make it even darker, and we save that, you'll see how this gets a lot darker. So if I want to make a smoky glass, again, I'll just put it back to 0.9. And it looks like this in path tracing, but then again in lit, doesn't feel as dark. We don't get those edges. And that's again because it's not properly ray traced. It's not as physically correct or calculated as accurately as it is in path traced mode. So again, you can compensate for that. Generally, like if you wanted to get the same look in lit mode, not path traced mode, you could take these values a lot darker, a lot lower, and that would kind of give you a similar kind of look. Like maybe if I went like 0.3 for all these RGB, so this is like a darker gray, then in lit mode, we should start to get a little bit more, and again, thickness will play a role as well. So if I did like 0.04 in lit mode, you know, now it's almost solid. Maybe let's try 0.4, 0.0, 0.1. Let's try that. You can kind of get a similar result. Now it's a little bit more see-through, but still fairly dark. Let's try 0.15. Right, so you can kind of get different looks, but it doesn't really match up with the path tracing settings. It'll be drastically different between the two. And again, if you want to kind of cheat that, maybe I'll also go back here and demonstrate that again. You can use the path tracing quality switch if you have to do something like that. So maybe if we put that into practice, like I need it to look similar in lit and path traced mode, I could kind of eyeball in and compensate for the differences. So maybe we'll do like 0.9, but then I will make this our path traced route, and then for our normal route, I will make it a lot darker, maybe like 0.25, multiply it by 0.25 so it gets a lot darker. And same thing for thickness, maybe thickness in path traced mode is going to be 2 to compensate so it looks similar in lit mode. Maybe same thing, I multiply it by 0.25. And you might have to change those values. There's no perfect conversion that I'm aware of. This is this kind of, in this case, maybe giving a visually similar result. So if I do those path trace switches, and I'll probably also have to, I think for thickness, I'll also have to make it even less. So over here, and you could probably do this better, I'll do something like normal, also multiply it by 0.25. And what we can end up with, let's space this out a bit more. If I do something like that, and again, it's not common where you'd have scenes that need to be both in path traced and not path traced, but here it is in lit, and here it is in path traced. So at least it kind of is similar. It's never going to be the same, path tracing always is going to look way better at the moment. But at least it's kind of reasonably in the same world. So you can kind of experiment like that if you needed it to work in both modes. Now what about a plastic like this? It's still see-through, but a little bit more softer of a highlight. Or what about something like silk? If you're part of the Patreon, which you can find a link to down in the description below, you'll get a PDF for this video that goes over doing a couple more samples of these materials. And if you become part of the Patreon, you also get the PDFs for many, many, many other videos I've done. Pretty much almost every video I do gets its very own PDF describing every step and describing a lot more additional details.